Welcome back. Section 6.3 now we're going for. Addition and subtraction of radical expressions. I'm going to have to make a lot more videos because we are done for this semester meeting face to face. It's all going to be online. So these are the lectures you have to go by. I think I had 2 students for chapter 5 send questions. I can't help you if you don't send specific questions when you start doing the problems. So we're going to do section 6.3 and then move on through all the way up to 6.6. And I don't know what we'll do about a test. We're going to do some form of a test. It's going to be different than the last one though. Alright, so addition and subtraction of radical expressions. This stuff isn't too bad. Again, terminology throws us off in math. Radical expressions, it just means something with a square root symbol, or a root symbol I should say. When we're adding and subtracting, you want to view the root symbol as a value. Now, when that is the same number, we know that square root of 3 equals something. We plug that in the computer, we get an answer. It's a decimal and nasty, but it's a value. So what we can do is think of square root of 3 as x. So if you saw 5x minus 4x plus 6x, you would know how to handle that right away. All they're doing is changing and making it a square root of 3. What happens is, you know that square root of 3 is a value. That doesn't change. We're going to leave it. It's a nasty value, so we leave it because it's cleaner to write square root of 3. We have 3 different terms that are multiplied by square root of 3. Just as we would have had 3 different terms multiplied by x, you combine them, we combine our terms and multiply by square root of x. So I'm going to go down here. We have a 5 minus a 4 plus 6. When we take 5, and it doesn't matter what order you go in. If we take 5 minus 4, we have 1. 1 plus 6 is 7. So we just write that as 7 square root of 3. We had 5 square root of 3s. We took away 4 square root of 3s. That gave us one of them. And then we added 6 square root of 3s. So if you start thinking of this as x, it makes life a lot easier when you're combining terms. Now, sometimes they'll give us 2 that are different. The whole key is find a perfect square or multiple perfect squares. But find perfect squares and pull them out, pull them out, pull them out. If you are left with something that's the same, then you can combine. So I'm going to take 3 square root of 8, and I am going to rewrite this. I'm going to factor it out, but I'm not going to factor it out in prime factors. You can if you want to, but that's work that you don't want to do. So I'm going to take and factor out by perfect squares. Can I get a perfect square out of 8? Well, I certainly can. I don't know the best way to, I'm going to write it this way. I'm going to go with the smaller, with my prime, so then it'll just stay there. 3 times square root of 2 times 4 equals 8. Well, then I can break that down further and see that there is, you can remember, real quick, you can rewrite these like this. Square root of 2, square root of 4. You multiply them together, you have a square root of 8. So you can think of each one of these separately. When you see a square root of 4, you know that you can pull a 2 out. When you pull a 2 out, you pull it out and you multiply it by whatever was in front. So 3 times 2. So what I actually have is 6 times the square root of 2. I'm going to do the same thing for 5 square root of 18. Now sometimes you might not see it. You might get a 6. You might say 6 times 3, and then you break down the 6 as 3 times 2. Then you'll see your 3's. If you see a repeating value, you pull one out. If you see 2 3's, pull one out. If you see 2 5's, pull one out. So you could factor that as 3 times 6 and then break the 6 down. Or you can just see that there's a 9 in there. 5 times square root of 2 square root of 9. Square root of 9 is 3. So I pull a 3 out and I'm left with square root of 2. So now what I have, since I'm adding, 3 square root of 8 is the same thing as 6 times the square root of 2. 5 times the square root of 18 is the same thing as 15 times the square root of 2. So actually, I have 6 times the square root of 2 plus 15 times the square root of 2. I can add those together and get 21 times the square root of 2. So, not bad. There's not too many things to know. The idea is that if this is the same, you can combine. So then when it's different, try to make one that's the same. You're looking for perfect squares. So see if you can get some perfect squares out of there. All right, let's do a couple more in 6-3 before we advance to 6-4. Hopefully you're finding joy in this. There's lots of joy to be had when working algebraic expressions. So my former intermediate algebra professor from KVCC used to say you'll be weeping tears of joy when you see an algebraic expression. I didn't believe him at first, but then by the end of the semester, I was nearly in happy tears. No, I wasn't, but I enjoyed it. Example 3. Now they say combine 7 times the square root of 75, so they give us a bigger number, and then they give us an x and a y cubed. So now they're talking about variables, which is no big deal because variables aren't any different than numbers. We're still looking for perfect squares. So what happens here is we've got to factor out and see if we can find a perfect square. Well, if you take your 75, it's easier for students to think money once you get 75s and 50s. So we can write 3 times 25. Again, I'll write the smaller number first. 3 times 25. Here, I'm ignoring everything else at this point. I'm just looking at what can I pull out. If we focus on numbers, if I see a 12, I can pull out a 3 and a 4, and I know square root of 4 is 2. I'm left with square root of 3. 75 is 3 times 25. Square root of 25 is 5. I pull it out. I have a square root of 3, square root of 3. That's the same. Now what I have to look at is this y cubed. Well, I'm left with a y times a y squared. There's my perfect square. There's my perfect square. There's my perfect square. There's a single and a single, so I leave those. So I'm going to rewrite this as 7. We can skip this. We can skip this. I'm going to rewrite this. I'm skipping a step. As 7 times 5, I'm pulling one out, times y. Y squared, square root of y squared is y. I pulled those out. I'm left with a 3, an x, and a y. The book guides you. Let the book guide you. X, Y. You know you're looking for an XY. If you don't have an XY, you can't combine anyway and you're done. There's no point in factoring out really. So the whole key is let the book help you determine what's going on here. So now I have a 4y and I'm going to pull out a 2. Square root of 4 is 2. In this case, that's it. I'm left with square root of 3xy. It looks nasty, but the key is find something that's the same. I did. 3xy, 3xy. I know my answer is going to be times 3x, square root of 3xy. I know it. That's my answer. I just need to figure out what all the stuff is in front. So I have 35y times square root of 3xy minus 4 times 2 is 8. So 8y times square root of 3xy, and I have a y, terms of y, terms of y, so 35 minus 8 y's. So 35, you could break it down even farther, and I won't do this again, but this is the thought process when you start combining. You have 35 y's and 8 y's, so you have 35 minus 8 y. So I have 27 y's times square root of 3xy. So again, the key is break them down and look for perfect squares. You're not necessarily looking for prime factors, although you can. What you're really doing is looking for perfect squares to pull out. So get those perfect squares out of there, and then multiply everything together. So we can do a couple more. Example 4 says combine 10 cube root. Okay, so they change it up a little bit. Now, let me write this one up, and then I'll mention a couple common errors here. Cube root of 27 AB squared. I would say probably the most common error is just missing the cubed, and a lot of students will just keep going with squares, and they'll have a 4 times 2 and a 9 times 3, and they'll try pulling the perfect square out and finding out they can't combine. You have to pay attention to the index. So cubed root. If this was squared, we wouldn't be adding anything together. Cube root, cube root. The key is, can I get the same? Can I get the same cube root left over? I know I'm going to have an AB squared. Like, there is no perfect cube. Whoops, squared. There is no perfect square of A. There's only one of them there. There is no perfect square of B, perfect cube of B squared, because there's only 2. You need 3 to get a perfect square. So I know I'm going to have AB squared left over under my radical. Here, I have my B squared that I need. I have A to the 4th. Well, A to the 4th is A cubed times A. The whole key, when your index is 3, you're looking for cubes. If your index is 4, you're looking for anything raised to the 4th power. So what I'm going to do is I'm going to rewrite. I'll take a couple extra steps in this just so you see. My 8, I know that I'm just going to write it. I know that's 2 times 2 times 2. There's my perfect cube. I want you to know that the perfect cube of 8, the perfect cube root is 2, and the perfect cube root of 27 is 3. Those are the 2 most common ones. I mentioned that in one of the other videos. So 2 times 2 times 2, and then we're multiplying by A cubed times A times B squared. That's that whole chunk. So what I have is 10 times 2 times A. When I have 3, I pull 1 out. 3, I pull 1 out. Perfect cube, the cube root of A cubed is A. Cube root of 2 times 2 times 2 is 2. And then I am left with the cube root of AB squared. Everything comes out. And then over here, I have 11A, and I'm just going to start pulling things out. 27. Perfect cube of 27 is 3. 3 times 3 is 9 times 3 is 27. That's times the cube root of AB squared. In this case, both of these numbers factored out completely. There was a perfect cube. So that's all that's left. I knew I was going to have that. Just so happens that's it. There's my answer for the radical form. Now all I do is I take my 10 times 2 is 20, and I have 20 A's. I'm just going to skip this. I have 20 A's, and here I have 33 A's. 11 times 3 is 33. 33 A's, I'm adding, there's no subtraction involved. I have A and A, so I can combine those. So I have 53 A's times the cube root of AB squared. I think we have time to do one more. So we'll do example 5 because it deals with a fraction. So we have an extra couple steps involved. I won't rush it. We're going to run over the 15-minute frame for YouTube, but we'll make it work. It'll just take a little longer to load it. All right. Square root of 3 over 2 times 1 square root of 3. In this case, I'll say step 1. We need to rationalize the denominator. Rationalize the denominator. This one's already rationalized. So our square root of 3 over 2, we're done. It's this 1 times 1 over the square root of 3. We need to rationalize that. So I'll take, I didn't realize my daughter got into these. I bet the orange isn't working. No, it is. Kind of. Nope. Don't yet let young children get a hold of your dry erase markers ever, or your whiteboard. All right. So remember, to rationalize the denominator, when it's squared, we multiply by itself. If it's cubed, we need to find what makes it a perfect cube. In this case, it's just squared. So I'm going to start with the one I already had, square root of 3 over 2. And then here, I'm taking square root of 3 times square root of 3, that gives me my 3. Now I have a whole number. I don't have a radical. I've got it rationalized. I'm done with that part. Up top, I do whatever I multiplied by the denominator to rationalize. I multiply by the numerator, so I have a square root of 3. However, we're talking fractions and addition. So even though these are the same, the denominator is different. So what I'm going to have to do is figure out how to get my LCD. With 2 and 3, my LCD is 6. It just means, what do I do to make this one 6? I multiply by 3. I'll do an extra step. I'll do it in red now that I got it in my hand. I multiply by 3. 3 times 2 is 6, so I do that on the top. 3 times 2 is 6, so I do that on the top. All right, just simple, regular rules of fractions. That's no different. What I end up with is 3 times the square root of 3. I'm going to take an extra step. Over 6 plus 2 times the square root of 3 over 6. And I don't want to reduce the lowest terms here, because if I do, I'm back to where I started. I've seen that happen. I've seen students go here and then they reduce the lowest terms and they get right back here. Right now, the reason we changed each one and got an LCD is so that we could combine the numerators. I have a square root of 3 and a square root of 3. I have 3 of them here, 2 of them here. So I have 5 square root of 3s over 6. And that's it for section 6.3. So in a little bit, I'll come back with section 6.4 for even more enjoyment and fun. I bet you're looking forward to that.